Hello friends. In the last class we discussed about natural convection over a vertical flat plate, laminar natural convection over a vertical flat plate, and we looked at the order of magnitude analysis and deduced the expressions for what the Nusselt number would depend upon for large Prandtl numbers and for small Prandtl numbers. Right. So we got that for large Prandtl numbers, the Nusselt number would actually depend on RAPR. So for large Prandtl numbers, the Nusselt number would depend on RA to the power of 1 by 4, whereas in small Prandtl numbers, it would depend on RAPR to the power of 1 by 4. So this is what we saw in the last class. So today, we'll be looking at the more detailed methods of solving the equations in order to get the expression for Nusselt number. So first we will look at the similarity solution method like we did for the force convection boundary layers over laminar force convection laminar boundary layers over a flat plate. In the same fashion, here also we can derive similarity variables if we can non-dimensionalize y with reference to the boundary layer thickness delta. Right. So we'll derive the equations and show how the solutions look like. Of course, they are ordinary differential equations and coupled with each other because in this natural convection, energy equation and momentum equation have to be solved simultaneously. So you get a coupled system of ordinary differential equations. So you cannot analytically solve it. It will be a numerical solution required for getting the solution of this. So what we will do is to look at the equations and then finally look at the expression for Nusselt number that is derived out of this and show that it also agrees with the orders of magnitude analysis that we looked at last class. Subsequently, we'll also look at the integral method in which we would assume velocity profile and temperature profile of a certain kind and then derive the expression for the. So you'll be assuming an approximate velocity and temperature profiles which will be fitted to the given boundary condition so that the Nusselt number closely matches with the exact solution. Okay, so this is basically what we will do today. And then further subsequently, we will be looking at constant wall flux boundary condition. Much of what we will be doing today is constant wall temperature boundary condition. We will be looking at constant wall flux boundary condition and turbulent boundary layers in the next class. So that's the plan for the remainder of natural convection. Okay, so let's move to the whiteboard now and start looking at the similarity solution for laminar flow over a vertical flat plate by natural convection. Okay. So the title of this topic itself is quite long. Right? So laminar natural convection over a vertical flat plate, and we are looking at similarity solution. So we know that in the orders of magnitude analysis, we looked at the delta, delta T by H goes as RAH to the power of minus 1 by 4. In both cases, delta T by H here also goes as RAH to the power of 1 by 4. There is also a Prandtl number there, which is okay. But in both cases, delta T goes as that, and delta T are only related through Prandtl number. Therefore, we know that both delta and delta T in these cases, delta as well as delta t. So delta by x as well as delta t by x go as Rax to the power of 1 by 4. Okay, so this is something that we already know. So if I would like to write y by delta of x, this would be y by x into, so this goes as Rax to the power of minus 1 by 4, sorry. So y by x times Rax to the power of 1 by 4 will be non-dimensional variable. Okay, so just a second. Okay, so this is one non-dimensionalization we'll do. So we'll say this is eta. So when I normalize y with respect to delta, since this is delta t also goes as the same Rax to the power of minus 1 by 4. So this will also be delta t will be the same variation with some constant. Okay, so that constant can be of course obtained when we do the solution. So we only normalize with respect to this. So the similarity solution remains similarity when we do this. Okay, so this is done. Then we also know that u goes as alpha by x into Rax to the power of half. Okay, so this is something which we have also seen somewhere here. Yeah, this is the delta t by h, and yeah, so this is the expression u by h. Yeah, u. So this is the thing that we are looking for. U goes as alpha by x into x by delta t to the power of 1 by 4, which will go as u h by alpha goes as Rax to the power of 1 by 4. So u goes as alpha by h Rax to the power of 1 by 4. So u at any x will go as alpha by x into Rax to the power of half. So this is r to the power of half. So that's what we looked at. So since this is the case, and if we define stream function psi such that del psi by del y equal to u and del psi by del x equal to minus v. So this is the usual definition of a stream function. Then we can normalize a stream function from this thing you will get. F, if I get as the normalized value of stream function, this can be written as psi by x into psi by alpha into Rax to the power of half. Rax to the power of minus 1 by 4, sorry. Okay, and we also define a non-dimensional temperature, theta. Theta is T minus T infinity divided by T wall minus T infinity. Now with all of these variables, if I start with u del u by del x plus v del u by del y is equal to g beta into T minus T infinity plus mu times del squared u by del y squared. So this is the momentum equation. The energy equation is similarly u del t by del x plus v del t by del y is equal to alpha del squared t by del y squared. Okay, so these two equations, if I try to substitute in terms of u is del psi by del y, and therefore this will be del squared psi by del y del x, and so on and so forth, and then try to normalize these and derive all of these equations so that you eliminate one of the independent variables and write it in terms of the combination variable eta. So what does this basically mean? If I have a boundary layer like this, then suppose this is my thermal boundary layer, the temperature profile, and this is my velocity profile that goes on that. Now this profile would basically be just scaled by the thickness of the boundary layer. So here it will be this and this, here it will be that, and as I go further higher, it will be this and this. So the whole thing basically is getting scaled by the delta of x. Okay. So this is at x1, let us say, this is at x2, and this is delta at x3. Then the whole profile will only get scaled by this. So that is the meaning. So these profiles are self-similar. Okay, this wall is T wall, T temperature at wall is T wall, and this is T infinity. And the velocity here is 0, as well as here is also 0, and here it goes to U max. So this is the velocity profile that prevails throughout the region, except in the very close vicinity of this one, the leading edge, where the boundary layer thickness delta itself goes to 0, so that's a singularity. But except that point, elsewhere the solution is self-similar, and therefore we can reduce these partial differential equations into ordinary differential equations only in x and the y dependence, sorry, only in y, and the x dependence can be observed. So this whole thing can be plotted as a single profile of eta versus f prime, which will be so because this is psi, so del psi by del y will be in terms of f prime, which is del psi by del df by d eta. So f prime versus eta will give me a velocity profile which goes something like this, and theta versus eta will have a profile which goes something like this. So this is basically, so this is the theta profile, and this is the f prime profile. So this is basically what I expect. So all of these get scaled to, on the eta scale, it will come to this. Okay, so this is basically what we mean by the similarity solution, and this is basically what we are trying to do. So when I do this and reduce these equations to ordinary differential equations, I get these two ordinary differential equations. One is f triple prime, so the del squared u by del y squared will actually become f triple prime minus 1 over pr times half of f prime square minus 3/4 of f double prime okay minus theta equal to 0. So this is one equation. The second equation would be theta double prime, which will basically be from this one, and minus 3/4 f theta prime, okay, is equal to 0. Okay, so these are the two equations that we will get. And what will be the boundary conditions for this equation? The boundary conditions will basically be defined from the velocity conditions. So at y is equal to 0, u is equal to v is equal to 0, and t is equal to t wall, and at y is equal to delta, okay, whichever is the larger of the two deltas, maybe in this case, t is equal to t infinity and u is equal to 0. Okay, so this is a condition that you will eventually get. So if I try to control this, or if I try to make this into the normalized variables here, then I'll have f is equal to 0 equal to f prime and theta is equal to 1 at eta equal to 0, because f prime equal to 0 basically means u is equal to 0, and since stream function needs to have a reference, we start with the 0 and the 1. So that is what it is. So this gives me f is equal to f prime equal to 0 at theta at eta equal to 0 and theta equal to 1. Similarly, in this one, you will actually get as eta tends to infinity. So this is as y tends to infinity, right? Theta is equal to 0 and f prime equal to 0. Okay, so this is f prime, so this goes to 0 and this goes to 0. So these are the conditions I have. So 1, 2, 3, 4 and 5 conditions. And since this is a third order equation, I'll need 3 conditions for this, and this is a second order equation, I'll need 2 conditions for this. So there are 5 conditions. So this problem is well defined, and I can go ahead and solve this. Once I have solved it, I'll be able to get the value of, so we'll be solving for f prime and theta, and f double prime and theta. So at theta and theta prime. So these are the 5 variables that we'll be typically solving for in this case. And with that, what we will get is that you'll be able to get f double prime at 0, which is going to be del u by del y at 0. This will give me CF, and theta prime at 0, which will be corresponding to del t by del y at 0, and this will give me this number. Okay, so this is basically how it is done. So you evaluate the gradients of velocity and temperature in the non-dimensional form, and then from that you can calculate the expression for this number. So using this, this actually was first solved by Simon Ostrach. So there is a NACA report in which he had solved this and published. So basically he found that for all cases, NUX would be equal to some function of Prandtl number divided by square root of 2 into grx to the power of 1 by 4. Where gr, the Grashof number, is defined as g beta into t1 minus t infinity into x cube divided by u square. Okay, so where g is acceleration due to gravity, beta is the coefficient of cubic expansion, t1 and t infinity are the temperatures, x cube, x is the x coordinate along the this is the x coordinate and this is the y coordinate. So x is the x coordinate along the plate, x cube divided by mu square. Mu is the kinematic viscosity, which is mu by rho. Okay, so now Ostrach actually tried to fit values of f of PR for various ranges of Prandtl numbers. So in the range of Prandtl number from 0.5 to 50, he found f of PR by root 2, of course, is 0.676 into square root of PR divided by 0.861 plus PR, whole thing is the power of 1 by 4. Okay, so if I substitute that here, then I'll get the Nusselt number in ux is equal to 0.676, the Grashof to the power of 1 by 4, I can take a Prandtl to the power of 1 by 4 along with it. So GRPR is RA. So GRXPR will be RAX, which will basically be, this will be multiplied by nu by alpha. So I'll get a nu alpha here, which is G beta delta T X cube divided by nu alpha. Okay, so that is the expression for RAX. So you will get this multiplied by RAX to the power of 1 by 4. So one Prandtl to the power of 1 by 4 has gone here, the other Prandtl to the power of 1 by 4 will remain here, divided by 0.861 plus PR, whole thing raised to the power of 1 by 4. Okay, so this is the solution that was obtained by Laminar Natural, and this is what we had published. Okay, so this you can take the limit as Prandtl number goes much greater than 1. So what you do is you take this Prandtl to the power 1 by 4 down. So what you will get is 0.861 by PR plus 1 whole thing raised to the power of 1 by 4 in the denominator. So since Prandtl number is much greater than 1, this will be much smaller than this. So you can neglect that term. So what you will get in the numerator is, so in the denominator there will be only 1 to the power of 1 by 4, which will be 1. And therefore this Prandtl has already gone here. So it will actually become NUX is equal to 0.676 RAX to the power of 1 by 4. Okay, so this is what we had found also in the order of magnitude analysis. When the Nusselt number goes much greater than 1, then when the Prandtl number goes much greater than 1, the Nusselt number is a function of RAX to the power of 1 by 4. This is what we got, and that we have confirmed here. Although this expression is not valid for much smaller values of Prandtl number, we can still try looking at that. So if you look at this, in this expression, when Prandtl number is much less than 0, this is much less than this term, so this can be omitted. So you will have a 0.861 raised to the power of 1 by 4. You divide this 0.676 by that, you get a number multiplied by RAX PR, the whole thing raised to the power of 1 by 4. So for Prandtl number much less than 1, you get NUX is about some constant multiplied by RAX PR, whole thing raised to the power of 1 by 4, which is also confirmed from our order of magnitude analysis. So the solution that Ostrach got from the exact solution of the ordinary differential equations fits to a function which obeys this scaling rule, that at large Prandtl numbers, Nusselt number is only a function of RAX to the power of 1 by 4, and at small Prandtl numbers is a function of RAX PR to the power of 1 by 4. Right? So that's respected in this case as well. Now let's move on to look at the integral method. So in the analytical solution that we just got, that is the similarity solution method, we have actually we were required to numerically solve the two ordinary differential equations, simultaneous ordinary differential equations, in order to get the Nusselt number and so on. So instead, if we want to do it more simply, then we assume simplified profiles. So assume U is equal to, or let's say U by U max is equal to A plus B y by delta plus C y by delta whole square plus D into y by delta whole cube. Okay, and in this we know that at y is equal to 0, we know U is equal to 0. Okay, and at y is equal to delta, we know that U is equal to 0 and del U by del Y also reaches 0, or rather y tends to infinity if you like. Okay, as we go far away from the plate. And at y is equal to 0, if I take the momentum equation, which is U del U by del X plus V del U by del Y is equal to g beta into t minus t infinity plus mu del squared u by del y square. In this, since u and v are 0, I'll be able to take these two out. So then this becomes this. So I can write g beta into t wall minus t infinity, because at y is equal to 0, t is t wall, minus or plus mu del squared u by del y square is equal to 0. Okay, so this is the condition that you will get in addition. So there are 4 conditions, 2 conditions at y equal to 0 and 2 conditions at y equal to y tends to infinity. So with these conditions, if I solve for the 4 constants a, b, c, d, then I will get this as equal to y by delta multiplied by 1 minus y by delta the whole square. Okay, so this is the expression that I will get, which will be u by u max. Now u max, as you understand, is the maximum velocity at any x. So at any x, there is a u max. So here there is a u max, here there is a u max, here there is a u max. So at any x value, there is a certain value of u max. So this u is actually a function of both x and y, and this u max is a function of x. And at any given x, that is, if I have the profile, at any given x, if this is delta, so this is the y coordinate. So if I normalize with respect to delta, then u by u max, the profile will go something like this. So this u by u max at any location will go in this fashion. So at this location, the u is equal to u max, so this whole thing will be 1. And at both ends, it will be 0, because here y by delta is 0, and here, at this point, 1 minus y by delta is 0. So it will be 0 at both of these locations. So that's what the profile that you are seeing is. Okay, so this is the thing. You can actually substitute these into this and calculate, and where you get actually u max is actually equal to g beta into t wall minus t infinity into delta square divided by 4b. So all of these are constants. This delta is a function of x, and therefore u max is a function of x. So this is the expression that you get. Okay, so u by u is actually equal to this multiplied by this is what you get. Okay. So that is the first profile, and we also assume similarly t minus t infinity divided by t wall minus t infinity is equal to 1 minus y by delta t the whole square. This also can be derived by assuming this is equal to a plus b y by delta t plus c y by delta t whole square with boundary conditions. T is equal to t wall and y is equal to 0, and t is equal to t infinity and del t by del y equal to 0 as y tends to infinity. Okay, so the temperature profile goes something like this. Okay, so if this is delta T, then the temperature profile goes something like this. Here it is T wall, and by the time it reaches this location, it reaches T infinity as well as the gradient goes to 0. So that is the expression that you would actually use. So as y tends to 0, this is y is equal to delta T here, right? Okay, so if you put this and substitute for these and simplify, then you get this expression. So it's a quadratic expression that we have chosen. Okay. So once we do this, we have these two approximate profiles. U by u max is this, and t minus t infinity by t wall minus t infinity is this. Now, if I substitute these two into the momentum equation and energy equation in the integral form. So what are the momentum and energy equations in the integral form? If I integrate the equation like we did in the force convection case also across the boundary layer, then I would actually get an equation which looks like d by dx of integral from 0 to delta, if I would, or can be infinity also, u squared dy is equal to g beta integral from 0 to delta of t minus t infinity dy plus, or rather this will be integrated, this will actually have mu del square u by del y square. When I integrate it with y, it will get mu times del u by del y at delta minus del u by del y at 0, right? So now del u by del y at delta, you know that del u by del y is 0 at delta, so this goes off. So you get a minus mu del u by del y at 0. Okay, so this is the expression that I get. So I can differentiate this to find out what is del u by del y at 0 multiplied by nu. Okay, so I'll get that expression as, we'll just do that now. So this is the momentum integral equation. I'll erase and write this with only the term that is non-zero. So it will look cleaner as the equation. So you get minus mu del u by del y at y equal to 0. So this is the first equation. The second equation, which is the energy equation, I integrate. I get d by dx of integral from 0 to delta of u into t minus t infinity dy will be equal to, again you get alpha times del t by del y at y is equal to 0 with a minus sign, right? So because it will be alpha del square t by del y square. So that is the second equation. So in these two equations, now I substitute for u from this profile and for t minus t infinity from this profile and all of these, and try to integrate. So I get this. And for these two, again I substitute these two profiles for evaluating del t by del y at 0 and del u by del y at 0 and simplify these equations. So let me do that. So what do I get from the first equation? D by dx of integral integral from 0 to 1, I write in terms of eta. So I have a u square, which is nothing but, if I write y by delta as eta, so that is eta square into 1 minus eta the whole to the power of 4. So eta into 1 minus eta the whole square is what you have here. This is eta and this is eta. So 1 eta into 1 minus eta whole square. So this square will be eta square into 1 minus eta whole to the power of 4, which is u by u max. So it will be u max square will come out of the differential. So I'll get a u max square here. Okay, multiplied by dy. Actually, if I write it as d eta, then and a delta will also come out here. Okay, so this will be my first term on the left-hand side. Okay, which is equal to g beta times integral from 0 to 1. Again here, integral from 0 to 1. If I write for t minus t infinity, I write t minus t infinity by t wall minus t infinity. I'll get t wall minus t infinity here. Okay, and then I'll get a 1 minus. And now what do? I write it as, before I go everywhere here again in the integral method, what I'm trying to do now is to assume delta is approximately the same as delta t. So this is one restrictive assumption I'm making in order to make the algebra simpler. I'll show you when this assumption is not made, the algebra becomes a little bit more complex, but it is still workable. So right now we'll do with this assumption. So this is the method which was done by Squire. Okay, so this was way back in 1950s that he had done this. So we'll just use that at the moment. So squares method. So you'll actually integrate between 0 and 1. So this will also become 1 minus eta the whole square d eta. And in order to write d eta, it's actually dy. I'll get a delta also here. Minus this del u by del y at 0. Del u by del y at 0 will actually be u max multiplied by u max and by delta multiplied by y by delta. Okay, so this will be the expression that I'll get. So this will be equal to u max by delta multiplied by, this is d by d eta of eta into 1 minus eta the whole square. So if I write this is eta multiplied by 1 minus 2 eta plus eta square at eta equal to 0. So at eta equal to 0, these two terms, so if I differentiate this, okay, so I get a eta minus 2 eta square plus eta cube. If I differentiate this, I'll get a 1 here minus 2 eta square will become eta, because eta square will become 2 eta, so it will become 1 minus 4 eta plus the eta cube will become 3 eta square at eta equal to 0. So this will be 0, this will be 0, it will be actually 1. So this whole term will be just 1. So I can write this as u max, and u will be there, u max by delta multiplied by 1. Okay, so that is the simplification that I have shown here. So that if I can actually remove this also. So I have just differentiated the assumed profile with respect to eta and found out del u by del y at y equal to 0 using the assumed profile. So this is the expression that I get. Now let's look at what this integral would actually become. So integral from 0 to 1 of eta square into 1 minus eta whole to the power of 4 d eta. So this is a little cumbersome to expand. So let me just assume z is equal to 1 minus eta. Okay, so then dz will be actually minus d eta. Okay, so if I substitute this as minus dz and take the minus here, then the limits will again change. So for z, this will be 1 to 0, but when I take the minus sign here, it will again become 0 to 1. So it will remain the same. So this would actually become the integral from 0 to 1 of 1 minus z whole square into z to the power of 4 dz. That's what we'll get. And now this I can expand it as 1 minus 2z plus z square multiplied by z to the power of 4. So it will be z to the power of 4 minus 2z to the power of 5 2z to the power of 5 plus z to the power of 6. When I integrate that, I'll actually get z to the power of 5 by 5, that is this one, minus twice z to the power of 6 by 6 plus z to the power of 7 by 7, integral limits between 0 and 1. So it will actually, at 0 all of these will be 0, at 1 it will be 1 by 5 minus 2 by 6 is 1 by 3 plus 1 by 7. Okay, so this is the expression that you get. So if I simplify this, this will become equal to 1 over 105. So if I take 3 into 5 is 15 into 7 is 105. So that will be 5 goes 21 times, 3 goes 35 times, and 7 goes 15 times, right? So you will get 21 plus 15 is 36 minus 35 is 1 by 105. Okay, so this is 1 over 105 that I have got. Similarly, if I integrate this expression, it is 1 minus eta whole square d eta from 0 to 1. So that will actually become 1 minus 2 eta plus eta square integrated between 0 to 1. This will actually become 1. So this will become eta minus eta square, 2 into eta squared by 2. So the 2 will get cancelled. So that will be minus eta square plus eta to the power of 3 by 3 between limits 0 to 1. So this will become 1 minus 0. This will also become 1 minus 0, and this will become plus 1 by 3. Okay, so this 1 and 1 get cancelled, so it becomes 1 by 3. So this gets integrated to 1 by 3. Okay, so let's now substitute this whole thing into the equation. So I get 1 over 105 of d by dx of u max square delta is equal to g beta t1 minus t infinity into delta divided by 3, okay, minus u max delta u max by delta. Okay, so let's call this as equation number 1. Now let us do the energy equation. The energy equation looks like d by dx of integral from 0 to 1 of u and t. T are both there, so this is actually u max into t1 minus t infinity, and then also be a delta that will come, and you will have eta into 1 minus eta whole square into 1 minus eta the whole square beta. Okay, so this 1 minus eta the whole square is the temperature profile, T by T minus T infinity by T1 minus T infinity. So you have a T1 minus T infinity into this, and this is U by U max. Okay, so there's a U max into this, which is U, and dy is delta d eta. So this is the delta that comes out here. So this is the left hand side, and this is equal to minus alpha times del T by del y, which will basically be T1 minus T infinity by delta multiplied by d theta by d eta at theta equal to 0. Okay, and this d theta by d eta is actually 1 minus eta the whole square, which will be 2 into 1 minus eta into minus 1, which will be at eta equal to 0. So if I put eta equal to 0, then we get a minus 2. Okay, so this term can be replaced by a minus 2. So it will be minus 2 into minus alpha is equal to 2 alpha into T1 minus T infinity divided by delta. Okay, so and erase this portion of it like I did last time, so as to keep it more clean. So this is, so you get a minus 2 for this. This is a minus 2. Now let's do the integration that is remaining to be done. So this is 1 minus eta to the power of 4. So the integral is integral from 0 to 1 of eta into 1 minus eta whole to the power of 4 d eta. So like the last time, that will be easier to simplify it by substituting z equal to 1 minus eta. So if I say z equal to 1 minus eta, then dz is equal to minus d eta. So if I substitute this with the minus dz, the minus will go here and change the limits. The limit, if I use for z, will be 1 to 0, it will again become 0 to 1, and eta will be 1 minus z. So this will be integral from 0 to 1 of 1 minus z multiplied by z to the power of 4 dz. So now that will become z to the power of 4 minus z to the power of 5 when integrated so this will give me z to the power of 5 by 5 minus z to the power of 6 by 6, right? Now, if I substitute the limits 0 for lower limit, so this is from 0 to 1, the lower limit, both of these are 0. In the upper limit, it will be 1 by 5 minus 1 by 6, which will actually be 1 by 30. Okay, so this becomes 1 by 30. Okay, so that integral is done. So now this whole equation now can be simplified and written as 1 by 30 d by dx of u max delta. Okay, this T wall minus T infinity is independent of x because it's a constant wall temperature and T infinity is also a constant, so it can be taken out, and this T wall minus T infinity, so you can actually cancel out the T wall minus T infinity from the two sides. So it will only have U max delta is equal to 2 alpha by delta. Okay, so this is equation number 2. Let me bring the equation number 1 forward. So that is this 1 by 105 into U max squared delta is equal to this. Now, in order to solve for two variables, so equations 1 and 2 are to be used to solve for two unknowns. And use which are U max and delta. Okay, so there are two options at this point in time for you. You can either use the order of magnitude analysis and write the x dependence of U max and delta here, or you can just assume something and evaluate what the powers are. Okay, let me do the second one. So let's assume that U max is some C1 times x to the power of m, and delta is equal to some C2 times x to the power of m. Okay, because we know that both of these are going to depend on x to the power of something. You know that delta by x goes as Rax to the power of minus 1 by 4, and similarly U max into h by x by alpha goes as Ra to the power of half. So this is something that we already know. So automatically the powers are determined from there, but we will still determine them from this analysis itself. So if I substitute these into equations 1 and 2, so what I'll get is I'll be able to differentiate this because this constants will come out of the equation and the x to the power will get differentiated. And what I should do is that for the equation to be valid for all x, I will need to equate the powers of x in all the terms. Okay, so what I will do, I will substitute, for example, in 2, which is right forward, okay, so it's right in front here, so we can do that easily. 1 by 30 multiplied by this U max into delta will be C1 C2 into x to the power of m plus n. Okay, so C1 C2 can come out here, so C1 C2 I'll write here into d by dx of x to the power of m plus n. So it will be m plus n into x to the power of m plus n minus 1. Okay, so that is the left hand side. This will be equal to 2 alpha divided by delta is what? C2 into x to the power of minus n. Okay, C2 x to the power of n in the new denominator, so it can rest here. So this gives me, if I equate the powers of x, it gives me m plus n minus 1 is equal to minus n. Or if I take the n to this side, m plus m minus 1 is equal to minus 2n. So this is one expression that I have. Similarly, if I substitute in the this equation, so this equation basically is 1 by 105. There will be a C1 squared C2 which will come out here, and this will be x to the power of 2m and x to the power of n. So 2m x to the power of 2m plus n. When I differentiate that, it will become 2m plus n into x to the power of 2m plus n minus 1. So I'll write that here. The one equation gives me 1 by 105 into C1 squared C2 into 2m plus n into x to the power of 2m plus n minus 1. Okay, and that should be equal to, let's go back here, g beta into t1 minus t infinity by 3 is all constant. This is c2 x to the power of n, and this will be again separate code. So let's write one by one. G beta into t1 minus t infinity by 3 into c2 x to the power of n minus u max and u max by delta. So nu multiplied by u max is c1 and delta is c2 into delta into x to the power of into x to the power of m minus n. So if I equate the powers, I get from here m minus n is equal to n, because this is equal to this. So m is equal to 2n. So if I use m is equal to 2n in this, 2n minus 1 is equal to minus 2n. So 4n is equal to 1. So n becomes 1 by 4. And since m is 2n, m becomes half. So what do you get here? This comes to x to the power of half. Okay, so let me not erase this. So u max is a function of x to the power of half, and delta is a function of x to the power of 1 by 4. So let's cross-check this with what we had got earlier in the earlier expression. Yes. So delta and delta t. So delta so this delta t by h has a where I get the dependence of rah to the power 1 by 4. So rah to the power minus 1 by 4. So delta t is of the order of x into rah x to the power of minus 1 by 4. Okay, let me write that in my expression here. So if I want to verify this, okay, delta or delta t, both are in the same order here, is of the order of x into rah x to the power of minus 1 by 4. So which I will write it as x multiplied by g beta into t1 minus t infinity into x cubed divided by nu alpha whole to the power of 1 by 4. Okay, because rah to the power minus 1 by 4, I wrote 1 by rah to the power of 1 by 4. So what happens here? The others are constant. X, this comes out here. So this I can take it out from here and write it as x to the power of 3 by 4, which goes as x to the power of 1 by 4. Okay, so if I take this as some constant, so this is some constant times x to the power of 1 by 4. That is what you get here. So this is verified. Similarly, you said u max into x by alpha is of the order of rah x to the power of half. This is what we had said earlier. Okay, so if I bring to the other side, so it will become u max is of the order of alpha by x times g beta into t1 minus t infinity to x cube divided by nu alpha whole to the power of half. So the others are constant here. I'll just take the x things here is proportional to x to the power of 3 by 2 divided by x, which is x to the power of half. So which is again verified. So m is equal to half and n is equal to 1 by 4 are both consistent with what we had got in the order of magnitude analysis. So that's why I said that you could take m and n directly from the order of magnitude analysis and put them, or you could have derived it from this also. So now you have one more equation which we have to confirm. So there is a 2m plus n minus 1 will be equal to n. So let me just write that here. 2m plus n minus 1 is equal to n. So now if this is half, it will become 1, and plus 1 by 4 minus 1 is equal to 1 by 4. So 1 and 1 getting cancelled, 1 by 4 equal to 1 by 4 is verified. So all three expressions confirm the mutual consistency. So we have got m is equal to half and n is equal to 1 by 4. The next thing that we will do is to go back to the very same equations, and now that the powers of x get cancelled, you get two equations in two unknowns c1 and c2. So let's write them down. It is c1 c2 by 30 into this is 3 by 4, right? So 3 would get cancelled, it will become 40 here, and this 2 can be brought down here, so it will become 80. So I can write this as c1 c2 divided by 80 is equal to alpha by c2. So you get c1 c2 divided by 80 equal to alpha by c2, or c1 is equal to, or c1 by 80 alpha is equal to 1 over c2 square. Okay. Now the other equation will basically contain the same c1 c2 expressions. So it will actually be c1 squared c2 into 2m plus n. 2m is 1 and n is 1 by 4. So this is 5 by 4. So if I have 5 by 4 on this, so 5 will cancel this to 21. So 4 is multiplying it to 84. So you will get c1 squared c2 by 84. And this is g beta into this multiplied by c2, and this is minus mu into c1 by c2. Okay. So now what do? I divide the equation throughout by c2. So this c2 will disappear, this c2 will disappear. I'll get a 1 by c2 square here, and that 1 by c2 square I'll substitute from the other equation. Okay. So basically that is what I'm going to do now. So this is c1 squared divided by 84 is equal to g beta into t1 minus t infinity by 3 minus mu times c1 by c2 square. So it is c1 squared divided by 84 is equal to g beta into t1 minus t infinity by 3 minus mu c1 divided by c2 square. Is that correct? So the c2 goes here, c1 squared divided by 84 because there is a 4 by 5, and yeah, so these x powers will get cancelled. Yeah, so that's it. So now if I substitute for 1 by c1 square, c2 square as c1 by 80 alpha, so this will become g beta into t1 minus t infinity by 3 minus mu into c1 squared divided by 80 alpha. Okay, so that's the thing that you get. So here this mu by alpha will become a Prandtl number, and there is a c1 square which I can get from here. So c1 squared multiplied by 1 by 84 plus Prandtl number by 80. Okay, so you take this side. This would be equal to g beta into t1 minus t infinity divided by 3. So I can bring this here and take square root. So c1 would actually be equal to g beta into t1 minus t infinity divided by 3 times 1 by 84 plus Prandtl by 80. Okay, this whole thing to the power of half. Right. So And this would be actually, if I divide it by 80 alpha, it will become C2 square, and I need C2. Okay. So C1 is equal to C1 by 80 alpha is equal to 1 over C2 square. That is equal to 1 over 80 alpha times G beta into T1 minus T infinity divided by 3 times 1 by 84 plus Prandtl by 80 whole thing raised to the power of half, right? So C2 into x to the power of 1 by 4. This is your delta. Okay. So this delta is C2 into x to the power of 1 by 4. So delta by x will be this by x. This will be C2 x to the power of minus 3 by 4. Okay. And that will be equal to, what will be there? This will be the reciprocal of this raised to the power of half. So it will be 80 alpha raised to the power of half multiplied by, in the denominator I'll get a G beta into T1 minus T infinity, and in the numerator I'll get 3 times 1 by 84 plus Prandtl by 80, okay, whole to the power of 1 by 4. Right, so that is the expression that I'll get. So now if I simplify this, this into x to the power of 3 by 4, right? X to the power of minus 3 by 4. So the x to the power of minus 3 by 4, if I take it here inside, then it will actually become an x cube in the denominator multiplied by or raised to the power of 1 by 4. So this will automatically go in here. Okay. So you have a G beta into T1 minus T infinity into x cube, and there is an alpha square here. Okay, because this alpha to the power of half, if I remove this from here and bring this here, it will become alpha square to the power of 1 by 4. Okay, so this is the expression. So let me now take this 80 to the power of half also inside and simplify. So or I can bring this out of the expression. So if I can try to simplify this, then I'll get this is G beta delta T into x cubed by alpha square, which is nothing but RAPR. So it will be RAXPR raised to the power of minus 1 by 4 multiplied by this 80 to the power of half multiplied by 3 to the power of 1 by 4 multiplied by 1 by 84 plus Prandtl by 80 to the power of 1 by 4. So if I simplify this, then I get this. So if I write, okay, this is your delta by x. Okay, Nusselt number is at any x is h into x by k, which will be actually if I write h into T1 minus T infinity, is equal to minus k del t by del y at y equal to 0. And if I normalize this, then I'll get minus k into t wall minus t infinity by delta multiplied by minus 2. Okay, so this is what I'll get, because we know that del theta by del y at theta equal to 0 is del theta by del eta at theta equal to 0 is minus 2. So this is the expression. So this t wall minus t infinity will get cancelled. So if I bring this k on this side, this is h is equal to this. Okay, so h by k into x will become an x. Minus and minus will get cancelled. That will become actually 2x by delta. Okay, so this delta by x is this. So basically you need to get 2 divided by this number, which will be the Nusselt number. So if I put this and simplify that, you can verify this. You will actually get 0.508 into RAXPR to the power of 1 by 4 divided by 0.952 plus Prandtl number whole to the power of 1 by 4. Okay, so this is index. Now this is the expression that you get from the integral method, and if you compare it with what we got by the Ostrach's method, that was 0.676 RAXPR whole to the power of 1 by 4 divided by 0.876 plus PR whole to the power of 1 by 4. This is the similarity. Okay, so this is the exact solution, right? This is the approximate solution that you have got. So actually the match is reasonably good, but the only problem that you get with the integral method is that the prediction of the boundary layer thickness is not always correct, particularly for so Prandtl number much greater than 1, delta and delta t are very different. So the boundary layer thickness is not correctly predicted by this method, but the Nusselt number prediction is reasonably good for practically the whole range of Prandtl numbers that we have got. Okay, so the Nusselt number prediction is reasonably accurate. So we'll now look at what happens if we don't assume the delta equal to delta t. Since we have already crossed 1 hour, so what we will do is to stop here in this lecture. In the next lecture, what I'll do is to take you through to the method when we don't assume delta equal to delta t. So you'll then have 3 unknowns, because delta is unknown, delta t is unknown, and umax is also unknown. So all these 3 unknowns will need to be obtained. So you need a third equation. So you obtain a third equation from the very same 2 equations, and then use those 3 equations to solve for the 3 unknowns. So it actually gives you a little bit more complex algebra, but then eventually it is feasible to do. So I'll just show you how to do that and how Bejan has done it in this book. So he has actually used a different kind of velocity and temperature profiles as compared to what we had used in today's class. So we'll look at that and then conclude the boundary layer flows of natural convection method. So after that, we can also look at the constant wall flux boundary layers and then look at turbulent. So in the next lecture, we'll try to cover the remaining topics with the